Good morning, physics students. This is an amazing demonstration. We're going to learn about heat exchange, again, talking about the different rate at which heat transfers. So here I have, for you to think about, this is a block of metal. It's black. That's important for heat conduction and so forth. This is just a kind of heavy black piece of metal. And this is an identical piece, also black, same size, same shape, but it's made of wood. So we have a light one and a heavy one, piece of metal, piece of wood, but two black squares. So what I'm going to do is take the identical ones. I tried to get as identical as possible. Two identical pieces of ice, and I'm going to place them on these black surfaces. Putting them on my countertop. This is room temperature, because, it's the room. And this is room temperature. And this is room temperature because they're in the room. So they're all the same temperature. I'm going to take ice cubes and I'm going to put them on the squares. And then I'm just going to time how long it takes them to melt. And what I want you to tell me, what you want you to predict, are they going to melt at the same rate, or is one of them going to melt faster than the other? We have wood, we have metal, and we have at the same rate. So what I'd like you to tell me is which one's going to melt first. Think about that for a minute. Which one's going to melt first, the wood or the metal? Or are they both going to melt at the same rate? Okay, so before we can answer the quandary about the pieces of metal, I need to introduce a couple of topics to you. So let's start with this new thought. How many sprints from rest to 5 meters per second would a 65 kilogram girl have to complete in order to burn 500 calories? So this doesn't appear to be related to what we've been talking about, how changing temperatures change sizes of things, lengths of things, volumes of things. But we have this idea here, which is calories. That's going to be the English unit. We don't use those. We'll convert those. But that is a form of energy, and that's kind of what we're talking about. So we have this form of energy, 500 calories. So we have the kinetic energy because the kid is moving. We want to burn 500 calories. Now that's not in the right unit, and I gave you this hint here. One capital C calorie is 1,000 lowercase c calories because the English system is super annoying. So if we have 500 capital C calories, then that's the same thing as 500,000 lowercase c calories. And 1 calorie is 4.816 joules. So if we multiply that by, you put 1 calorie on the bottom, 4.186 joules on the top, and multiply those things, and you end up with a gigundous number, joules. Now we should write that in scientific notation. 1, 2, 3, 4, 5, 6, 2.183 times 10 to the 6th joules. So that's 500 calories. We have this many joules. That's what we're trying to get to. How many sprints do you need to take to do that? So we have our velocity is 5 meters per second, and we have a 65 kilogram girl. So the mass is 65 kilograms. Do you remember how to find kinetic energy? Wow, it has been a while since we've done that. Kinetic energy is equal to 1/2 mv squared. One sprint is this much energy. So the kinetic energy for one sprint is 1/2 65 times 5 squared. So you plug that in your calculator. 1/2 times 65 times 5 squared is 812.5 joules. That's joules per sprint. But we need to get to this many joules. So we're going to have to take the total energy needed, 2.093 times 10 to the 6th joules, and divide it by 812.5 joules to figure out how many sprints that takes. And if you take the time to do that math, I believe you get over 2,500 sprints. Now, is this reasonable? 2,500 sprints to burn 500 calories? No, because a sprint is more than just moving a mass at that change in speed. I mean, you've got muscles that are moving, you're breathing, you've got your heart beating. All of those are energy uses also, so that's using energy. It wouldn't take that many, but it still takes a lot. As far as just moving an object, that change in speed, that's the amount of energy that you get. How is that related to what we're talking about now? But this is the concept, kind of equating kinetic energy to calories. Energy in thermos process we're going to talk about today is calories. Calories is the amount of heat needed to change 1 gram of water 1 degree Celsius. When you look on the side of any kind of food label and it's talking about calories, that's what it's talking about. The amount of heat needed to change 1 gram of water 1 degree Celsius. You're made of a lot of water, but you're not changing temperature because of your water. You have other substances, and other substances take more or less amount of heat. It doesn't take the same amount of heat to change a degree Celsius as it does to change, a coffee cup a degree Celsius. Different substances have different amounts of heat that it takes to change. That is going to be called the specific heat. The specific heat of a substance tells you how much heat it takes to change its temperature. So you have a handy-dandy reference table that has a whole bunch of specific heats on it. And if you happen to notice, some ever so subtle ones are highlighted on mine. So specific heats are going to say how much the temperature changes. Let's come back over here. This is the equation we're going to be using for the next few homework assignments. Q is equal to mc delta T. It might look familiar from chemistry class. Q is for no reason good at all, the letter that we use for heat. That consistently needs to be measured in joules. M stands for mass. That needs to be measured in kilograms. Delta T stands for the change in temperature. And you can leave them in degrees Celsius. We would usually change things to Kelvin, but they change the same amount. And capital C is going to be the specific heat for whatever substance you happen to be talking about. Specific heat's unit is joules per kilogram degrees Celsius, I believe. I'll edit that if that's not what it is, but it seems like that should work. Okay, physics students, now I have a bit of a question for you. Based on our reference tables, we have here, I added a couple because of my chart. We have some specific heats for aluminum, copper, iron, brass, and nickel. So there are specific heats. And I want to know, based on Q is equal to mc delta T, the amount of heat that you put into something is going to make the temperature change based on the specific heat. I want to know if I put the same amount of heat onto 4 identical bars. So the trick here is I need to get wax to be suspended at the end of these bars. That's not easy to do while taping, but we'll try here. So we've got wax on the end of all of those, and I'm going to carefully pick it up, and I'm going to place it over the heat. And my question for you is, which one of those is going to melt first? I'm going to put the center of it over the flame, and if you can't read what those are, on the left we've got aluminum, and then the second one is brass, and then the third one is nickel. I don't know if that's focusing or not. And then the fourth one is iron. So we've got aluminum, brass, nickel, and iron. And I'm going to hold this over the flame, and based on their specific heats, can you predict which one's going to come first? You'd see the Bunsen burner, and this would happen a lot faster, but here we go. This is kind of pretty, so we'll just stare at the candle flame. Can you see anything melting? Is anything happening? No, not yet. Oh, there it is. We seem to have aluminum down. So, I would like you to tell me why in the comments. Aluminum is the first to melt. Does that make sense? Does it not make sense? So here we have our metal thing. Here's our aluminum. with a specific heat of 900. Here is 380, 440, and 448. So if Q is equal to mc delta T, why does this one melt first? That seems counterintuitive to me. I mean, most of my demonstrations don't work, so that could be it. But it's on the same amount of heat because the heat was in the center. So if this needs to stay the same, why, if this is the biggest for aluminum, if this is the biggest number, then it seems like the change in temperature needs to be the smallest. Because, I mean, they're not the same mass, but they're pretty close to the same mass. So it seems like there should be the least change in temperature in this one. But that's not what happens. Because science. First, these are all really similar to each other. This one obviously melted first. But there's another concept besides just specific heat. That concept is on table 11.3. It's called thermal conductivities. And if you look at these numbers, they are really small for iron. And the other ones aren't here, but they're also really small. And aluminum has a high conductivity, which means if you put a little bit of heat on aluminum, it will shoot through it much more quickly. So even though all of these are on the same heat source, aluminum actually is transferring the heat much faster. So that means it's actually getting more heat. It's actually taking in more heat, the aluminum is, than the other samples. I have one more quandary for you to answer in order to get credit for this video. All right, so here's our little demonstration. I'm going to take 2 pieces of ice, place them almost identical times. There's my piece of wood. Here's my, oh, wow, did you see that? Here's my piece of metal. Look at that. I'm going to have to put a ring around this one so that it stays on it. That's the winner. The metal one is going to melt much, much faster. The question is, why? So, I'd like you to comment back in the Google Classroom. They are both room temperature. This is the same temperature as this, same temperature as the counter, but for some reason, this ice cube melts faster. It is the same temperature, same size ice. It has nothing to do with that. It has something to do with the type of material. Tell me why and how the metal is melting that ice so much faster. That's what you should answer in the comments. And that is all for today. I will see you on Tuesday at 3:30 for our next Google Meet, where we will begin the next homework assignment. Have a wonderful evening. Don't do drugs. Go wash your hands.